This short video will explain how interrupts work on ARM Cortex-M microprocessors. Why do we need interrupts? Let me use a simple example to explain the reasons. On the STM3214 Discovery Kit, there are two LEDs, and a joystick with 4 push buttons. Suppose we want to develop a software program. If we press a button, the software turns on the red LED. In the previous lectures, we have learned how to configure GPIO output to control the logic state of an output pin, and how to program GPIO input to read the logic state of an input pin. There are two ways to monitor the logic state of an input pin, which is attached to a push button. One is polling, and the other is interrupt. The polling method is like picking up your phone every few seconds to check whether you are getting a call. The interrupt method is like waiting for the phone to ring. Apparently, the interrupt method is more efficient. You are free to do whatever you should do, and pick up the phone only when it rings. Here is a simplified pseudocode of the polling method. In the while loop, software constantly reads the input of the pin attached to the push button. It won't exit the loop until the button is pressed. After the program exits from the while loop, it turns on the LED. The polling method is a busy waiting approach, in which the processor repeatedly reads the input until the button is pressed. It is easy to see, the polling method is simple but inefficient. The interrupt approach is much more efficient than polling. If the user presses the button, an electrical signal, called interrupt request, is generated. When the processor receives the interrupt request, it automatically suspends the execution of the regular program, and starts the execution of a special defined function called interrupt handler. After the interrupt handler completes, the processor restarts the execution of the regular program from where it was stopped. Why do we call it an interrupt? Because the execution of the regular program is suspended, and the processor is forced to take care of an interrupt request. This video explains how interrupts work. Let's quickly review the memory map. The memory address of ARM Cortex-M has a total of 32 bits, supporting 4 GB of memory space. The memory space is divided into 6 different predefined regions. Each region is given for recommended usage. The first region is code region. It is primarily used to store program code. It can also store data. The code region is on-chip memory, typically on-chip flash. The size of on-chip flash is limited to half a gigabyte. The actual size of the on-chip flash varies based on different vendors and different chips. The second region is static random access memory, SRAM. It is primarily used to store data, such as heaps and stacks. We can also put code here. It supports half a gigabyte. The third region is peripheral. These peripherals include AHB peripherals, such as GPIO, and ADC, and APB peripherals, such as timers, and USART. The next region is for external device, such as SD card. The next is external RAM, which is executable region for data. It is off-chip memory, primarily used to store large data blocks. It has a total of 1 gigabyte. The last one is system region, which includes the NVIC, system timer, system control block, and vendor-specific memory. The internal SRAM region is assigned a space of half a gigabyte. However, the capacity of on-chip SRAM is often very small. For example, on-chip SRAM on STM3214 has only 96 kilobytes. The SRAM is divided into several segments. The initialized data segment. It contains global and static variables, which the program gives some initial values. The zero initialized data segment. It contains all global or static variables, which are uninitialized, or initialized to 0, in the program. The heap segment. It holds all data objects, which an application creates dynamically at runtime. The stack segment. Stack is used for various purposes. For example, The stack can store local variables of subroutines, save the runtime environment, and pass arguments to a subroutine. The stack is placed on the top of the internal SRAM memory, and it grows downwards. The heap is placed at the bottom of the free memory region, and it grows upwards. The stack and the heap are located at the opposite end of the free memory region. They grow in the opposite direction. In this way, the stack and the heap can take full advantage of the available memory space. When the stack meets the heap, free memory space is exhausted. While the code space can have as large as half a gigabyte, much of this space is reserved or not used. For example, STM3214 chip has only 1 megabyte on-chip flash memory. The memory address of the on-chip flash memory starts at 8 million in hex and ends at 80FFFFF in hex. Typically, the on-chip flash memory stores the initial value of the stack pointer, the interrupt vector table, the text section, the read-only data section, and the read-write data section. The text section consists of binary machine instructions. The read-only data section that defines the value of variables that cannot change at runtime. The read-write data section that sets the initial values of statically allocated and modifiable variables. In addition, a small memory region starting at 8 million in hex is mapping to the lowest memory region starting at the address of 0. In other words, two addresses can point to the same data item in this mapped memory region. This mapping region includes the initial value for the main stack pointer and the interrupt vector table. The nested vectored interrupt controller, NVIC, prioritizes and handles all interrupts. When we press the push button connected to the pin PA3, the hardware generates an electrical signal, called interrupt request, EXTI3. When NVIC receives the interrupt request, it forces the processor to jump to, and execute, a special piece of code, called an interrupt service routine, or an interrupt handler. Specifically, the processor will execute the function named EXTI3IRQ handler. The entry points of all interrupt service routines are stored in a special table. This special table is called an interrupt vector table. The interrupt vector table is stored at a predefined area in the memory. For ARM Cortex processors, the interrupt vector table starts at the memory address 4. By default, the interrupt vector table is mapped to the lowest address of the internal flash memory. However, software can remap it to a different location, such as internal SRAM. To understand interrupts, the concept of interrupt vector table is very important. The interrupt vector table holds an array of memory addresses. Each entry in the interrupt vector table is 4 bytes long. Each entry contains the starting memory address of an interrupt service routine. To put it simply, the interrupt vector table holds an array of function pointers. Every type of interrupt is assigned a number, called interrupt number. The interrupt number is used to index into the interrupt vector table. When interrupt X is triggered, NVIC uses the interrupt number X as the index value to look up the interrupt vector table, finds the memory address of the corresponding interrupt service routine for interrupt X, and forces the processor to jump to and execute this interrupt service routine. How does the NVIC controller use the interrupt number to look up the interrupt vector table? The first word in the memory is the initial MSP value. Here is the main stack, typically located in SRAM. The second word in the memory is a pointer to the reset handler, which is the starting memory address, or called entry point, of the function reset handler. The reset handler contains program code, which is executed when the processor is reset. Typically, the reset handler performs some hardware initialization first, and then calls the main function. Immediately after the processor is reset, the program counter is initialized to this value. For ARM Cortex-M processors, if the interrupt number is N, The pointer that points the interrupt service routine of interrupt n is stored at this address in the interrupt vector table. For example, the interrupt number of EXTI3 is 9. Then, the address of EXTI3 IRQ handler is stored at the memory address 64 plus 4 times 9. The result is 100 in decimal, or 64 in hex. Suppose the handler for external interrupt 3 is stored at the memory address 080030C in hex. In the interrupt table, the value 080030D is stored at the location 64 in hex. If the XDI3 interrupt request arrives, the NVIC controller will read the word stored at the memory address 64, and then set the program counter to that value. In this way, the NVIC controller forces the processor to jump to the interrupt service routine, EXTI3 IRQ handler. Note that, the least significant bit of these memory addresses is 1. When the processor jumps to a new code, it examines bit 0 of the destination address to determine the processor state. In general, for ARM processor family, if bit 0 of the destination address is 1, the processor will be in the thumb state. If bit 0 is 0, the processor will switch to the ARM state. However, for ARM Cortex processors, the bit 0 of the destination address must always be 1. This is because ARM Cortex processors only support thumb instructions. Please pay attention that the interrupt number can be negative. For example, the interrupt number of system timer, SysTick, is -1. Here is the interrupt vector table of STM3214. The first word holds the top of the main stack. The next 15 words hold the pointers of 15 system exception handlers. The next are pointers to vendor-specific interrupt handlers. The size of the interrupt vector table varies among different processor chips. Let's use an example to see how NVIC handles an interrupt. Suppose external interrupt 3, EXTI3, arrives at this time instant. Assume software has already enabled EXTI3 interrupt. An interrupt can be enabled by setting the corresponding bit in the interrupt enable register. The interrupt number of EXTI3 is predefined as 9. As you see from the interrupt enable register, external interrupt 3 has already been enabled. The interrupt priority register shows that the priority of external interrupt 3 is set to 2. NVIC first writes 1 to the pending bit of external interrupt 3 in the interrupt pending register. Let's assume the floating point unit, FPU, has not been used in this example. Then, NVIC automatically starts to the stacking process and pushes 8 registers to preserve the running environment. If the floating point unit is used, more registers are pushed into the stack during the stacking. NVIC first pushes the program status register, XPSR, onto the stack. Then, pushes the program counter, PC, which is register 15. Pushes the link register, LR, which is register 14. Pushes register 12. Then, register 3. Register 2. Register 1. And finally, pushes register 0. Note that, ARM Cortex uses full descending stacks. If a 32-bit item is pushed onto the stack pointer, SP, is decremented by 4. After NVIC pushes these 8 registers onto the stack, the size of the stack increases by 32 bytes, and the stack pointer is decremented by 32. This stacking process is automatically performed by the NVIC controller, not by the user code. Then, NVIC looks up the interrupt vector table, and finds the starting address of the interrupt service routine for external interrupt 3. Next, NVIC changes the status of interrupt 9, from the pending state to the active state. After that, NVIC forces the processor to branch to the interrupt handler, and starts to execute the interrupt handler. The interrupt service routine completes its execution by running the following instruction: BXLR. The instruction, BXLR, informs the NVIC controller to perform an unstacking process. At the same time, the active bit, in the interrupt active register, is cleared. The unstacking process automatically pops the values of these 8 registers out of the stack. Therefore, NVIC recovers the processor's state, or called running environment, to the time instant immediately before the interrupt handler starts. Let's see how the unstacking process works. First, NVIC pops register 0 off the stack. Then, pop register 1, register 2, register 3, register 12, the link register, the program counter, and, finally pop the program status register off the stack. After unstacking completes, the running environment has been fully recovered from the stack. All registers have their original values, as if the interrupt has never happened. As a result, the processor can successfully continue to execute the user program, which has been interrupted by the external interrupt 3. Let's see how the NVIC controller handles multiple interrupts. Suppose interrupt request 9, EXTI3, arrives at this time instant. NVIC first performs stacking, and pushes these 8 registers onto the stack. Then, NVIC forces the processor to execute the interrupt service routine for interrupt 9. Suppose another interrupt request, DMA1 channel 2, arrives, before the interrupt service routine 9 completes. In addition, this new coming interrupt has a higher urgency than the current interrupt being served. As you see from this table, the interrupt priority value is 3 for interrupt 12, and 5 for interrupt 9. Note that, for ARM Cortex processors, a lower priority value actually represents a higher urgency. Accordingly, NVIC has to respond to the new coming interrupt. Because the new interrupt has a higher urgency, NVIC then stops the current interrupt service routine, and performs another stacking. Again, it pushes another set of 8 registers onto the stack. Note that these 2 sets of registers have different values. The first set holds register values for the user program. The second set holds register values for the interrupt service routine 9. After the stacking, NVIC starts to execute the interrupt service routine of the new coming interrupt. The process of stopping the current interrupt handler and starting to serve another interrupt is called interrupt preemption. After the interrupt service routine 12 completes, NVIC performs unstacking, pops out 8 registers from the stack, and recovers the running environment for the interrupt service routine 9. Then, NVIC continues the execution of interrupt service routine 9. After the interrupt service routine 9 completes, NVIC performs unstacking to recover the running environment of the user program. After unstacking, the user program resumes the computation. In the previous example, we have shown that an interrupt with higher urgency can preempt an interrupt with relatively lower urgency. What would happen if the new coming interrupt request has a lower urgency? Suppose external interrupt 4 has less urgency than external interrupt 3. If external interrupt 4 arrives before the external interrupt 3 handler completes, NVIC won't respond the new coming interrupt request. Instead, NVIC will continue the execution of the current interrupt service routine. After the current interrupt service routine completes, unstacking and stacking are performed, before the new interrupt service routine starts. As you notice, the middle unstacking and stacking processes are unnecessary in this example. Therefore, ARM Cortex-M deploys an optimization technique, called tail chaining, to reduce the interrupt latency. Typically the unstacking process takes 12 cycles. The stacking takes 12 cycles too. However, the tail chaining takes only 6 cycles. Please visit the book website for tutorials and project templates.